A warm welcome to the third session of the National Seminar, India, Mathematics and Ramanujan, organized by Department of Mathematics. We are so lucky that we have such an eminent mathematician, Professor Shanta Laishram, as today's resource person. It gives me great pleasure to introduce Professor Shanta Laishram. He is currently a professor of mathematics at Indian Statistical Institute, New Delhi. His research interests are in number theory and related areas in mathematics. He has a number of publications in international refereed journals. He has delivered invited lectures at a number of universities and institutes in India and abroad, and has visited more than 20 countries for academic related work. After schooling in JNV, Taubal district, Manipur, BSc from DN College of Science, Imphal, he joined Tata Institute of Fundamental Research, Mumbai, directly for PhD in mathematics, and he was awarded TAA Memorial Award for the Best PhD Thesis in Mathematics 2007-8 at TFR Mumbai. After his postdoctoral research at University of Waterloo, Canada, and short academic visit to Max Planck Institute for Mathematics, Bonn, and ETH Zurich, he joined ISER Bhopal initially and later shifted to ISI Delhi, where he has been there for the last 10 years. He was awarded Microsoft Young Faculty Award 2010-11 and have got a number of fellowships from different organizations, including INSA and ALGNT, and he has been involved mentoring students at different levels and is also a research co-guide at IIT Delhi and Manipur University. He is an associate member of Mathematical Olympiad Activities and National Board of Higher Mathematics. Now, Dr. Laishram loves nature, reading and traveling, and takes a keen interest in the latest happening in the world of environment and politics and other social issues. Today, he will give a talk about Ramanujan Primes. With this brief introduction, on behalf of Department of Mathematics, now I invite Professor Shanta Laishram sir for his talk.
Yeah, thank you very much for your nice introduction, and I'd like to thank you and the whole department for the kind invitation to speak here. So today I'll be talking about the notion of Ramanujan Primes. Today I'll be talking about the Ramanujan Primes. So I'm going to define what's a Ramanujan Prime and talk about some results in this direction. First, let's so let's go to this. Okay, so I'm going to tell you something about this primes. So ancient Egyptians were probably the first and the earliest people to have knowledge about the prime numbers. So all of you, of course, know what is a prime. So I'm just going to give a brief history, whereas I'm going to go very fast. The first time when these primes were studied with the results is Euclid's Elements around 300 BC, where there's a famous theorem of Euclid on infinitude of prime and fundamental theorem of arithmetic were discussed. And of course, in the last few centuries, a lot of work has been done relating to primes. All of you, of course, know about Fermat's little theorem and Fermat's last theorem. But around 17th century, most of the work on prime numbers was done. So after Fermat, there's been a long list of people: Euler, Legendre, Gauss, Riemann, and of course our Ramanujan, who did a lot of work related to prime numbers. So here I want to give an emphasis about this. I just want to talk about this. I want to give you information that Ramanujan's work on Riemann zeta function, it gave a completely new dimension for studying about prime numbers. In fact, like the prime number theorem by Hadamard and de la Vallée-Poussy, actually it came up as a related, something related to work of Riemann, and Of course, all of you know about the holy grail of number theory, the famous Riemann hypothesis, which is still open, and which has a which has a big connection to the study of prime numbers. And of course, there are many other ways to study prime numbers about this about the sequence of prime numbers. Like, you can talk about different properties, many things, but I won't go into everything. I won't go into those things. Today I'm going to talk about something related to the work of Ramanujan. And in fact, as the name suggested, Ramanujan is coming to picture. And so I'm going to look at the distance, about the existence of prime number in certain intervals, and talk about the Ramanujan primes. So all of you know the famous this conjecture of Bertrand's, which is now known as Bertrand's postulate. So it tells you that given any number n bigger than 1, there's always a prime number p with between n and 2n. So for example, if you take 10, between 10 and 20, there's a prime number. So in fact, there are at least one prime number, 11, 13, 17, 19. There are in fact 4 prime numbers. But the Bertrand's postulate, it tells you that for every integer n bigger than 1, there's always a prime number between n and 2n. And this is a very well-known result. This was first proved by Chebyshev in 1850 by using analytic number theory ideas. And there's been a lot of other proofs. Erdős in 1932 gave a calculus-free proof. So he gave a proof which doesn't involve calculus, which just relies on the combinatorial arguments and binomial coefficients. What I'm interested today is on the work of Ramanujan, where he gave another proof of this Bertrand's postulate by using Stirling's formula. So all of you, of course, know Stirling. If you have studied calculus, you know Stirling. So Stirling formula tells you that n factorial is like n by e power n. So now let me come to more precise statements. Okay, given a number x, for any real x, let pi x count the number of primes up to x. So for instance, if you take x to be 100, then pi of 100 is 25, because there are 25 primes up to 100. And as you can see, the prime number changes at positive integers. So the value of prime numbers, so if primes are positive integers, of course, so it will change only at positive integers. So that is very easy thing to know. The famous prime number theorem tells you that between up to x, there are around x by log x primes. So if you want to be more precise, so limit of pi x divided by x by log x is 1 when x goes to infinity. So the well-known prime number theorem tells you that the limit pi x log x by x actually when x goes to infinity is this 1. So this is the famous prime number theorem. But so we're going to use this prime number theorem, of course, but in a certain way. So I want to start with this work of Ramanujan in 1919, where he proved that in fact between x by 2 and x, there are infinitely many primes. So basically when x goes to infinity, number of primes between x by 2 and x goes to infinity. So what he actually proved is the following result. So if you remember that pi x counts the number of primes up to x, then pi x by 2 counts the number of primes up to x by 2. So pi x minus pi x by 2 means number of primes between x by 2 and x. So it counts the primes bigger than x by 2 but less than or equal to x. So what he proved is that pi x minus pi x by 2 is bigger than 1 over log x times x by 6 minus 3 root x, whenever x is bigger than 300. Now as you can see, the right hand side of the inequality is an increasing function of x. So when x goes to infinity, the right hand side goes to infinity, and that's why the left hand side goes to infinity. So that proves that's what Ramanujan proved. So pi x minus pi x by 2 goes to infinity when x goes to infinity. What it tells you is that number of primes between x by 2 and x is of the order of x by log x. Basically some constant times x by log x. So this is what Ramanujan proved. So far so good. So in fact, after this, I mean, of course, Bertrand's postulate, there has been like many other proofs and people have used it in left and right in many places. After this work of Ramanujan, so Sondo actually came up with this work. So before I tell you about the Ramanujan, Ramanujan Primes, let me just tell you about Bertrand's postulate once again. So what Ramanujan proved is that between x by 2 and x, there are infinitely many primes when x goes to infinity. So Bertrand's postulate tells you that between n and 2n, there's at least one prime. So Bertrand's postulate is equivalent to showing pi of 2n minus pi of n is bigger than or equal to 1. Now Ramanujan's result tells you that between x by 2 and x, there is at least, I mean, there's at least one prime when x is bigger than 300. So let me just go to this result of Ramanujan. So the left hand side of the inequality here, pi x minus pi x by 2. Yeah, so left hand side of the inequality, pi x minus pi x by 2. Yeah, so this is an integer. It's either 0 or positive number. And the left side is a real number. So if the real number is positive, then the left side is at least 1. Right? So in particular, when x is bigger than 300, the left side is, the right side is actually positive. That means left side is at least 1. So that is how Ramanujan proved the Bertrand's postulate. And since the difference pi x minus pi x by 2 changes value only at positive integers x, you need to check for values positive integers between x less than or equal to 300. So basically you check for x equal to 2, 3, 4, 5 up to so 300 to see that there's always a prime between x by 2 and x. So in fact, what Ramanujan obtained is that for all real number x bigger than or equal to 2, there's always a prime between pi x and between x by 2 and x. So this is the proof of Ramanujan for Bertrand's postulate. Now after this work of Ramanujan, I mean, of course, and Bertrand's thing, quite a bit of generalizations has been done. So around 2009, Sondo actually he re-looked at the proof of Ramanujan, and in fact Ramanujan result can be used to obtain that for a given positive number n, you can find a x naught n such that whenever x is bigger than x naught, there are at least n primes between x by 2 and x. So what I'm saying here is the following. Since the left hand side, this pi x minus pi x by 2 goes to infinity when x goes to infinity, that means that whenever x is bigger than some x naught, the number of primes, the value pi x minus pi x by 2 is bigger than or equal to n. From here, Ramanujan this Sondo defined the Ramanujan primes as follows. So for n bigger than or equal to 1, the nth Ramanujan prime, which we denote by Rn. So Rn means the nth Ramanujan prime. So this is the least positive integer Rn with the property that whenever x is a real number bigger than or equal to Rn, there are at least n primes between x by 2 and x. So as you can see, the statement is statement is very simple. So it's the least positive integer Rn such that once x is at least equal to or more than Rn, then there's a prime between x by 2 and x. And in fact, Ramanujan's proof of Bertrand's postulate tells you that the first Ramanujan prime is actually 2. All right. So we have the first Ramanujan prime is 2. So yeah. So let's now try to see that. I mean, so when Sondor defined the Ramanujan primes, he doesn't say that Rn is the least prime, but it says that Rn is the least positive integer. Least positive integer. Now let's try to show that in fact Ramanujan primes are primes. So what Ramanujan prime tells you that whenever x is bigger than or equal to Rn, this number of primes between x by 2 and x is at least equal to n. Now we'll show that Rn is a prime. The way to show Rn is a prime is that we started with let's take a prime which is the largest prime less than or equal to Rn. So Rn, P is equal to Rn if Rn is a prime. Otherwise, P is the prime which is less than or equal to Rn, and P is the largest such prime. Then what we know is that number of primes up to x. Okay, whenever you take x between P and Rn, so number of primes up to x is same as number of primes up to Rn, which is same as number of primes up to P. And also number of primes are increasing function, so number of primes up to P by 2 is less than or equal to pi of x by number of primes up to x by 2 is less than or equal to pi of Rn by 2. From here, what you can derive is that for any x between P and Rn, the number of primes between x by 2 and x, so that is pi x minus pi x by 2 is bigger than or equal to pi of Rn minus pi of Rn by 2, which is actually bigger than or equal to n, right? But then what is our Rn? So Rn was the least positive integer such that this inequality that pi x minus pi x by 2 is bigger than or equal to n for x bigger than or equal to Rn. And if I take P to be largest prime less than or equal to Rn, still this inequality is valid. So hence the minimality of Rn implies that Rn has to be equal to the P, which is the largest prime, I mean less than P. So that means Rn itself is a prime. From here we can now give a new definition of Ramanujan prime. So Rn, the nth Ramanujan prime is the least prime Rn with the property that whenever x is bigger than or equal to Rn, then number of primes between x by 2 and x is at least n. So that is the Ramanujan prime. Okay. Now I go to some more properties of Ramanujan primes. So the first property is that Ramanujan prime is actually a prime. The next property is that Ramanujan prime has a nice property that you see between Rn by 2 and Rn there are exactly n primes. So what we know is that between x by 2 and x there are at least n primes whenever x is bigger than or equal to Rn. So what we are going to prove is that when x is equal to Rn, it's exactly equal to n. So that means pi of Rn minus pi of Rn by 2 is n. So suppose on the contrary, let's assume that number of primes between Rn by 2 and Rn is bigger than or equal to n plus 1, right? Then what we have is that, you see, Rn is a prime, so number of primes up to Rn minus 1 is exactly equal to number of primes up to Rn minus 1, and Rn is odd, right? Primes are odd, so Rn minus 1 by 2 is even. So what we know is that number of primes up to Rn minus 1 by 2 is actually equal to pi of Rn by 2. So hence what we know is that pi of Rn minus 1 by 2 minus pi of Rn minus 1 by 2. So pi of Rn minus 1, number of primes up to Rn minus 1 minus number of primes up to Rn minus 1 by 2 is actually equal to number of primes up to Rn minus 1 minus pi of Rn by 2 from the above above equalities, and with our assumption is bigger than or equal to n. But then what is our Rn? So Rn is the least positive integer such that whenever x is bigger than or equal to Rn, there at least x by between x by 2 and x there's always there's at least n prime. So this contradicts the minimality of Rn. So what this tells us is that our assumption is wrong. That means pi Rn minus pi Rn by 2 is actually equal to n. So there are exactly n primes between n by 2 and Rn by 2 and Rn. So this is the second important fact about Ramanujan primes. Now the third property is this, the fact which I have written on the written over there. So Rn is the maximum prime P with the property that there's at least n prime, exactly n primes between P by 2 and P. Okay. So if you have any prime such that number of primes between P by 2 and P is bigger than n, then P cannot be Ramanujan prime. So in other words, so let's try to prove it. Let Q bigger than Rn be a prime such that there are exactly n primes between Q by 2 and Q. Okay. Then what we know is that if you take any number x, any real x between Q minus 1 and Q, then since Q is exactly bigger than n, so x is bigger than Rn. So x is bigger than Rn, which implies that pi of x minus pi of x by 2 is bigger than or equal to n. Now on the other hand, whenever you have x between Q minus 1 and Q, now what is pi of x? Pi of x is same as pi of Q minus 1, which is pi of Q minus 1. Because Q is a prime, so number of primes up to x is exactly number of primes up to Q minus 1. However, pi of x by 2 is same as pi of Q by 2 because you see Q is odd, so Q minus 1 is even, so number of primes up to x by 2 is same as number of primes up to Q minus 1 by 2, which is same as number of primes up to Q by 2. From here, what you secure is that pi of x minus pi of x by 2 is actually pi of Q minus 1, because pi of x is pi of Q minus 1 minus pi of Q by 2, which is n minus 1. This is a contradiction because Q is exactly strictly bigger than Rn and x is the number between Q minus 1 and Q. Therefore, what it tells us is that Rn is the maximum, so largest prime with the property that pi of P minus pi of P by 2 is n. That means number of primes between P by 2 and P is actually equal to n. So by using this property, you can compute the first few Ramanujan primes. So the first Ramanujan prime is 2. The next Ramanujan prime is 11. After that 13, 29, 41, 47, 59, 67, 71, 97. So the first 10, you know the first 10 Ramanujan primes. Now the question which we're interested is that how do we compute Ramanujan primes? Of course these are primes, but how do we compute? Now one way is, of course, you use Ramanujan's result between x and x by 2. So actually there's a typo here. Between x and x by 2, there's at least 1 by x times x by 6 minus 3 root x. This value for x bigger than 300. And the right hand side is an increasing function of x, as you can see. So if you want to compute Ramanujan primes, so for example, if you want to compute R2, you check when this number 1 by log x times x by 6 minus 3 root x is less than is bigger than 1. Once it's bigger than 1, since it's a real number and left hand side is a positive integer, it's at least equal to 2. And at 392x, when x is 392.39, you get that the right hand side is exactly equal to 1. So for x bigger than 393, the number of primes between x and x by 2 is actually at least 2. So R2 will be less than or equal to 393. And for primes with all primes less than 393, you check when there's exactly 2 primes between p by 2 and p. You find that the maximal such prime is at p equal to 11. So you use those property. So Ramanujan Primes is the maximum prime such that number of primes between p by 2 and p is exactly n, right? You use those property. So this tells you that at 11 you find this p, you find it largest. So R2 is actually equal to 11. So here I want you to observe that even at 7, pi of 7 minus pi of 7 by 2 is 2. But R2 is not 7 because pi of 10 minus pi of 10 by 2 is 1. So similarly, we can compute the first few values. So you have R2, then you can compute R3, R4, etc. All right. So this is how you compute the first few Ramanujan primes. Of course, this method won't work well when you want to compute a big Ramanujan prime, but at least for the first few values, it will work well. So now the question which comes is that, okay, you have a Ramanujan prime, which is a prime which depends on n. Now, can you give a, of course, upper and lower bound? Can you give some bounds? How big is the Ramanujan prime? How small is the Ramanujan prime? So Sondo actually in 2009 he proved the following estimates. He proved that Ramanujan prime lies between 2n log n and 4n log n. So for any n bigger than or equal to 1, you know that Ramanujan prime exists 2n log 2n and 4n log 4n. Now let's take small p1, p2 be the sequence of primes. So p1 is 2, p2 is 3. These are sequence of primes. So the 2n prime is actually, so Sondo's result tells you that the nth Ramanujan primes lies between the 2n prime and 4n prime. So p of 2n means 2n prime and p of 4n means 4n prime. So he made a conjecture that in fact nth Ramanujan prime should not be that far, it should be less than 3n prime. So this is the conjecture of Sondo in 2009. So I proved this conjecture. So in 2010 I proved the conjecture by in fact showing that given Rn is less than the 3n prime for all n bigger than or equal to 1. In fact, I proved better estimates. What I thought was that given epsilon positive, you can give a bound on the nth Ramanujan primes as follows. So nth Ramanujan prime is less than 2 plus epsilon times n log n for n bigger than n naught epsilon. So where n naught, so whenever n is bigger than some number depending on epsilon, so the nth Ramanujan prime Rn is less than 2 plus epsilon times n log n. So here n naught epsilon was given explicitly. Yeah, so this is the result I have. So explicit result. So let epsilon be positive and choose whenever epsilon is less than 1.08, you define n naught epsilon to be x of c by epsilon log 2 by epsilon. So here you choose, so here the value of c is given by the table I'm showing you here. So when epsilon is between 0 and 2 by 11, you take c to be 4. When epsilon is between 2 by 11 and minus 4, and 0.4, you take c to be 5 and so on. And when epsilon is bigger than 1.08, then you have defined n naught to explicitly. Anyway, so you don't have to worry about remembering this. My point is that so nth Ramanujan prime is very close to 2n log n. So this is my result. So if you take epsilon to be 1, when epsilon is 1, so c is 8. And also use the fact that ith prime is bigger than or equal to I log I. That comes from prime number theorem, or the estimates from prime number theory that ith prime is less than I log I. you actually obtain that n at Ramanujan prime Rn is less than 3n prime for n bigger than or equal to 1. So this is the conjecture of Sondorf, which I proved it. All right. So after this, of course, there has been quite a bit of work. Now the question is that how far, I mean, how closely you can, I mean, get a bound for this Ramanujan primes. So another consequence of my theorem, which is the consequence, is that the n at Ramanujan prime is less than 2n plus epsilon prime whenever n is bigger than n epsilon. So yeah, so basically instead of going all the way to 3n, I can show that okay, so n at Ramanujan prime is strictly less than some 2n plus epsilon prime. So this was also proved by Srinivasan and Exler gave another proof, in fact, and they got some other estimates which are actually more or less the same estimate I obtained. Now, so it doesn't stop here. So after seeing my after the conjecture, then Sondorf, Nicholson, and Noye in 2011. So yeah, so what we know is that the n at Ramanujan primes prime lie between 2n prime and 3n prime. So then they wanted to look at the ratio. Okay, what is Rn by 3n prime? So far, any questions?
Sir, there is a question in chat box.
Yeah. Okay.
How to find epsilon in your proof of bounds of Ramanujan primes? How do you get
yeah. Okay. So in fact, yeah. So in this, I'm not finding epsilon. What I'm saying is that given epsilon, okay. So yeah, given epsilon, n at Ramanujan prime is yeah. So n at Ramanujan prime is less than 2 plus epsilon times n log n. So whenever n is bigger than n naught epsilon. So basically, you can, I mean, you cannot make, for example, R of 3, you cannot make it very close to 2n log n. But when n is sufficiently large, you can make it very close to 2n log n. That's what I'm saying. So we're not finding epsilon. So given epsilon, we're finding n naught epsilon.
maybe n epsilon, n naught epsilon?
Yeah. So I've given a, in fact, I've given a proof. I mean, not the. I've given explicitly what is n naught epsilon. So n naught epsilon is x pop. So e to the power c by epsilon times log 2 by epsilon, where I've stated c. Okay. So in fact, I've given it explicitly. Okay. Any other questions? Okay. All right. So maybe then I'll go ahead. Yeah, so if someone has a question, please for me. Now, after, yeah, from my results, Sondorf, Nicholson, and Noye, they computed the maximum of Rn by P3n, and they found that the maximum value is when n is 5. So, in fact, Rn by P15, sorry, yeah, Rn by P15 is 41 by 47 is 0.8723. In fact, what they showed was that for n bigger than 169,350, the maximum value of Rn by 3n is less than 13 by 15. So then, in fact, use my results. So this is quite easy consequence of my results. Some bit of calculus and analytic arguments. And so then look at the figure. So if the maximum value is when n is 5, where it's 0.8723, and after n less than when n is different from 5, the maximum is less than 13 by 15, and when n is also yeah, after 5, the next maximum is when at n equal to 10. So it comes at 0.8584, which is 97 by 113, and when n is different from 5 and 10, maximum value occurs at 11 by 13, which is 0.8461. What actually they prove is that when n goes to infinity, Rn by the 3n prime, the limit goes to 2 by 3. Yeah, so with some bit of analytic arguments, they could show this. So what it tells you is that if you take the difference, if you take the ratio Rn by 2n prime, so it looks like it behaves like 2 by 3, 3n prime divided by 2n prime. So from the above ratio, what you actually obtain is that Rn by p2n is like 2 by 3 3n by 2n. All right. So from their computations and observation, they made the following conjecture. So for m is given by 1, 2, 3, etc., they define nm to be like, when m is 1, they define nm to be 1, when 2, 1, 2, 4, 5, when m is 3 and 4, 1, 18, 9, etc. And they show that, and when m is bigger than or equal to 20, nm is 2. And they conjecture that number of primes up to mnth Ramanujan prime is less than m times number of primes up to nth Ramanujan primes, whenever n is bigger than or equal to nm. So this is the conjecture. This is quite an interesting conjecture. I mean, basically, does not only gives a bound, but it counts okay, up to mnth Ramanujan prime, how many primes are here. So in fact, they verified it for all whenever Rmn is less than 10 power 9. So whenever Ramanujan prime is bigger than 10 power 9, they verified it. Whenever m, of course, here, so they take m as 2, 3 up to 20, and the mnth Ramanujan prime is 10 power 9, and they verified it. So what actually they prove is that number of primes up to mnth Ramanujan prime is less than m times pi Rn. And Yang and Tokbei in 2015, they confirmed this conjecture. Yeah, so whenever m is bigger than or equal to 2 and n is bigger than 10 power 300, they confirm it. So basically, if n is bigger than 10 power 300, this is true. But unfortunately, if you want to use the computer, we cannot, I mean, we cannot go up to 10 power 300 by computer because it's too big a number to be tried computationally. So we need to, still the conjecture is open. That means for n less than 10 power 300, we still need to work on. Now here I want to update a conjecture in the sense that the conjecture of Sondo is not entirely true, in the sense that if for m less than 38, if you take n to be 9 and for any and some m, then this pi of like number of primes up to 9m Ramanujan prime is not bigger than or equal to I mean, yeah, so yeah, not bigger than or equal to m pi of R9, not less than m times pi of R9. So in fact it's bigger than. So the updated conjecture should be number of primes up to mn Ramanujan prime is actually less than m times number of primes up to Rn for all n bigger than nm, except when n is 9, m is 38. So this is the updated conjecture. So in a unpublished work so far, so in a work which I did with Anita Srinivasan, who is right now in Madrid. Actually, yeah, so we saw that we saw the trueness of this conjecture in the sense that we saw the number of primes up to mn Ramanujan prime is less than m times pi of Rn. So we proved the conjecture is complete totality. Sorry, yeah. So number of primes up to so this is true except when n is 9 and m is less than or equal to bigger than 39. So basically, in case of n is 9, you have to take m to be bigger than 39. So we actually we prove a more general result in the sense that we gave a complete very interesting upper and lower bounds for the number of primes up to n Ramanujan primes as follows. So the upper bound we defined by rho u of n and lower bound by rho l of n. Where rho l of, if you see these two expressions, they differed only by the part that in the so here plus kappa by log 2 and minus kappa by log 2. So so we are going beyond the log 2 factor. So here log 2 means here log 2 means log of log n. So log 3 means log n, log n. So this is our thing, our results. So basically we try to give as closely as possible the bounds of the Ramanujan primes. So here I've mentioned some kappa. So the kappa is actually I've given the value. So if n is bigger than 5,000, you take kappa to be 0.6. If n is bigger than 10,000, you take kappa to be 0.45, and so on. When n is bigger than 6, add 3 by 2, you take kappa to be 0.15. In fact, there's a history behind why kappa is coming in this. It comes from the computational results, computational ideas. All right, so I guess my talk, my talk is still 6:15, so I won't be able to give a complete proof, but I'll try to sort of give some flavor of the proof. I mean, the proof is not difficult. In fact, it's not easy either, because but not too difficult. But what we rely a lot of results from prime number theory and quite a bit of computations to get these results. What we did, so they prove by connecting a number of, we collect a number of results from prime number theory and computations, and by doing a very intricate analytic arguments, we actually prove it. So I won't give a complete proof, but I'll just show a glimpse of the proof, some ideas of the proof. Yeah, so the first thing is, and I won't go to the proof, but I want you to show the lemma. So basically at first I proved, so that I just said computationally that if n is less than 84745, this conjecture part is true. So you don't have to worry about this, because this is just bit of computation. And we didn't do it, basically from the verification of Sondo it follows. And another thing is that, if Mn is less than 500, this conjecture is true. So this some sort of computational result. So from my earlier results and bounds on the Ramanujan primes, so we can actually see this bit of computational result. So number of primes up to n Ramanujan prime divided by 2n is bigger than 1 plus 1 point something. So the point depends on how, so basically we expect it's very close to 1 when n is quite big, but up to 5,000 I've given you explicit values. I gave you both upper and lower bounds. Okay, and this is a very crucial key lemma which comes from prime number theorem, which was instrumental in our proof. Basically, from the deep results of prime number theorem, we actually know that number of primes up to k, so the kth prime pk is bigger than k times log k plus k times log k plus k log k minus 1 plus log k minus 2.1 by log k. So this is true for k bigger than or equal to 3. And again, so this is the upper lower bound. So the upper bound is also a similar thing. So the difference is only when that instead of 2.1 here you have some ck, where I have listed you the values of ck. So so we cannot get better than 2.1 in the upper in the lower bound, but in upper bound we can go, or we'll try to go somehow very close to very close to 1. So this results actually follow from the work of Pierre Dussat and others. So there's a lot of computational related work on this bound, so we rely on their results. And yeah, so the another consequence of this result of theorem 4, I mean, so yeah, this is the one, and we also need this result. So basically, I want you to recall that theorem 4. So theorem 4 gives you a sort of upper and lower bounds of the number of primes up to nth Ramanujan prime, and by working with this, I mean, and doing a bit of analysis, we also obtain that number of primes up to Rn by 2n is less than 1 plus with some constants. So yeah, so we use this sort of things, so we combine with this, and yeah, so I won't actually give you the, I mean, the proof is not difficult, I mean, but we need to do quite a bit of checking. Now, okay, so I want you to now recall theorem 3. So we won't go to proof, but we'll use theorem 4 to give a proof of theorem 3. So proof of the theorem 3, what we wanted to prove is that number of primes up to mn Ramanujan prime is less than m times number of primes up to nth Ramanujan prime. This is true for all n bigger than or equal to nm except when n equal to 9, where we take m to be bigger than or equal to 39. So nm I have defined it here, you can see. So this is what we wanted to prove. All right, so yeah, so let's try to give some ideas of this proof. So the first thing is that we use a sequence of steps to go to a bit larger m and n. So first we want to dispose of small m and n. So you start by taking n to be bigger than 3, bigger than nm, and also m is bigger than 39 when n is 9. So to prove that pi of Rmn is less than m times pi of Rn, so we observe that this is actually equal to is equivalent to pi of Rmn by 2mn is less than or equal to pi of Rn by 2n. So we want to sort of see this. So as you can see from here, yeah, you can expect. So when you try to prove something like this, so I mean something like this inequality, so you observe this. Then what you do is that you somehow yeah, so get a very good upper bound for this, which is less than a very good lower bound for this, and work out. So somehow play around. That's so that is the quite a very intricacy part. So you have to get, like, for a given n, for any m, so you sort of try to get a very delicate bound which is less than the lower bound for pi of Rn by 2n. And so this is our work. So I've defined this nu so nu of n to be pi of Rn by 2n. So our aim is to show that, in fact, to prove the theorem, this is what we need to. Pi of nu of mn is less than nu of n for all mn. Not all mn, I mean those conditions. So so first, by using this, some of the lemmas I've given you, use lemma 6 to show that if n is less than 80, mn is bigger than 500. So then again, so you take n less than 80, then you use some bit of not only computations but some bit of earlier results to show that that is not possible. And further you use lemmas 5, 7, 8, 10, and of course number every time you keep increasing. So at n less than 80 is not possible, then n is bigger than 80. So you get suppose n is up to 500, then you, by using some arguments, you remove it. It's not a brute force computation, but by using this lemmas, and you keep on going in sequential steps. Finally, you derive that For the proof, we can assume n is bigger than 5,000 and mn is bigger than 1 lakh. So this is the first thing. So from now on, we are going to assume that n is bigger than 5,000 and mn is less than is bigger than 1 lakh. So to show that nu of mn is less than nu of n, basically you need to show this inequality. Okay. So I made some, here analysis is coming into picture. Now kappa u, you put it as log 2 plus 1 plus k2. Then kappa l is log 2 plus 1 minus kappa by log 2. So then what we need to show is that from the above to show the above inequality, actually you need to show that 1 plus log m by log n times 1 minus log 2n minus kappa l by log n plus log, this is bit of analysis here, log 2mn minus kappa u by log mn minus 1 is positive. So the last expression on, in the screen, it should be positive. This is what we need to show. So if you show this, the conjecture is true, the proof is complete. Then again, you sort of play around with this, see what you can do. So you somehow rearrange these terms and so that the left hand side, this expression is bigger than this, some expression. So you're separating m and n. All right. So so after that, and you have to show that this part is actually positive. So so to show that that part is positive, actually it suffices to show that log m is bigger than the expression on the right. And right now n is bigger than 5,000, mn is bigger than 1 lakh. So what I did is that since n is bigger than 5,000, so you see that the right hand side or left hand side here, so this is the decreasing function of n. So and when n is 5,000, you actually get this 1.2 by log 2 times this. You sort of play around with this, and it's less than log 13. So the inequality 5 is valid whenever m is bigger than or equal to 13. Now, so we have to take m is less than 12. Now we also know that n has to be bigger than 84745 by one of the lemma. So if n is less than 84745 is true. So n is bigger than this, then again you use somehow this. You prove this. You see that this inequality is in fact less than log 2, and you prove the theorem. So here a bit of analysis coming in. So once you prove theorem 4, theorem 3 follows easily. The more complicated part is the proof of theorem 4. So here we follow the proof of Turkmen-Yang, and in fact we rely on these properties of this Ramanujan primes, that half of the S Ramanujan prime is bigger than S minus n Ramanujan prime, and in fact P of Sn, like if you take n Ramanujan prime to Ps, then P of S minus n is less than half Ps minus less than P of S minus n plus 1. Then you use the estimates of the Ket prime and somehow play around with this. You have quite a bit of, in fact, you define these functions coming from the prime number theory estimates, where you have this some C naught here. I won't go into much detail here because it gets quite, it's delicate and a bit complicated. So here, in fact, from the property f of s is positive and g of s is negative, and somehow okay, so you saw that f is decreasing for n bigger than c naught x by 2, and g is also decreasing for n bigger than c naught x by 2, and so just play. Basically quite a bit of very intricate analysis is required to show that so the inequality we wanted. Okay, so yeah, so that's all. So here are some of the references, and the first result, I mean, Sondo's, the papers of Sondo actually first appeared first in American Math Monthly 2009, and then later on this result in Journal of Integer Sequence. My paper was in International Journal of Number Theory. Then, then Anita's paper was also in integers. And in fact, so there are quite a bit of playing. So one can also generalize this. In fact, there's been a lot of work on generalizing this Ramanujan prime. So you can actually talk about derived Ramanujan primes, etc. So like the way you define Ramanujan prime, you take the set of Ramanujan prime and sort of see certain properties. And there have been a lot of work on that too. So I will stop here for today. So thank you.
Sir, is there a similar result as for prime number theorem?
Similar to, yeah, I mean, yeah, of course. So yeah, in fact, there's been also work. Yeah, so between two Ramanujan primes, is there like between Rn and 2Rn is there Ramanujan prime extra? So there have been certain results, but of course, like our result. So basically, the result which we have produced, the theorem shows. So this is sort of a prime number theorem for Ramanujan prime, in the sense that you are talking about number of primes up to nth Ramanujan prime. Obviously, so it's like I mean there are around 2n primes between nth Ramanujan prime. So what people have studied later on is that when you look at derived Ramanujan primes, then you talk about, so not only that you are asking, so derived Ramanujan prime is so between Rn and Rn plus 1, there's at least n Ramanujan prime. So not Rn, so R prime n and R prime 2n, there's at least n Ramanujan prime. So there are there's some results, but so far the result about it similar to prime number theory is this result that I quoted.
We can expect, because it is as n log n is approximated to Pn, something related to this is also there. No?
Yeah. Yeah, but in fact here it's a bit more complicated, but yeah. So but then we rely on our estimate from prime functions. If we get better estimates in the prime counting function, then we will get better here.
Shanta, this is Srini.
Yeah, hello Srini.
Hi. Nice talk here. Talk. So I have a question.
Yeah, please tell me.
From Rn,
Yes.
how far you go to catch hold of another prime? See, you are computing the number of primes, at least n kind of thing, right?
Yes.
But suppose I want to catch hold of only one prime.
Okay, I mean not necessarily Ramanujan prime, right? Any
Not
prime.
necessarily Ramanujan prime.
Okay.
A prime.
Yes.
Is there any result like that?
Well, then it comes to this difference between consecutive prime, because Ramanujan primes is itself prime. So I don't think there's any result about it. Because Ramanujan prime is prime. So the next prime will be definitely then it comes to our estimates about gaps between primes.
I see. Okay. For example, in the Bertrand postulate kind of thing, so it says between x and 2x there is at least one prime, right?
At least one prime, yeah.
So, but x to 2x, this is a large gap. See,
large gap. So, yes.
But if you use the Riemann hypothesis, you can go up to x to the power half plus epsilon.
In fact, right like if you use Grimm's conjecture, you can go to x to the power 0.49. This 0.4, yeah. So less than half.
Yeah. So that's by conjecture. But Riemann hypothesis, if you use, you can go up to x to the power half plus epsilon.
Yeah, that's true. Yeah, that's correct.
So similar kind of things are there for this, for your kind of thing, for Ramanujan.
Yeah. So in fact, yeah, if you just look, I mean, like look at this. So next prime which appears after Rn, then there's nothing much. But if you like, there's been some results on. Okay, so when's the next Ramanujan prime? So there has been some results.
Okay.
But the next prime, of course, nothing except, I mean, like whatever we know about the general prime. That's
okay. Good talk.
Okay, thank you, sir.
Yeah.
So, okay, thank you so much, sir. So, let me invite Miss Adila for casting vote of thanks.
Good afternoon. Good afternoon, all. Miss, am I audible?
Yeah.
Yes. Yes.
Okay, this was our second day of the national webinar on India, mathematics and Ramanujan. We have been very fortunate to have Professor Shanta Laishram sir from ISI Delhi to lead our third academic session. We are so grateful to you, sir. He actually talked about the Ramanujan Primes, and he also described certain conjectures and theorems related to that topic. When he stated a conjecture and gave his own proof, I was really happy, and I felt very lucky to listen a piece of mathematics from its creator himself. It was really great listening to you, sir. I would like to extend our sincere gratitude on behalf of my department and myself for accepting our invitation and spending your precious time with us, sharing your knowledge and expertise on these different topics. And I would also like to appreciate his constant effort and for explaining things as simple as possible for the young learners to understand and grasp completely. We really thank you, sir.
Okay, thank you.
I would also like to extend our thanks to the organizers of this webinar, our head of the department, Dr. Preeti ma'am, Dr. Sini miss, and all other organizers who worked behind this webinar. I would also like to acknowledge the efforts and I would also like to acknowledge the active participation of each and every one of us present here, teachers, research scholars, and all other young learners who actively participated and cooperated with us and collectively contributed to the huge success of our program. We are really thankful. Thank you all.
Thank you, Adila. Sir, very nice to meet you. So, hope we will meet again.
Yeah, so, okay, thank you very much. And
thank you, sir. Thank you so much.
Okay, thank you. Then I'm leading the session.
Sir, our faculty members are here. Dr. Sinipi, she is now, her radio is on. Mubina, Dr. Mubina,
okay.
You may be able to see them.
Hello. Hopefully, post pandemic, I can. So,
Professor,
Calicut, is it near the state's home or?
yeah, very near the case. So, Professor Raji Pilakat is here, and Professor Anil Kumar also is here. His video is not on. Somebody want to ask something. Malaya here.
Yes, ma'am. Good afternoon, sir.
Yeah,
Good afternoon.
So many 5 minutes I'm trying to talk, sir, but my microphone is not working, so again I join now.
Okay.
Sir, my doubt is in your proof that about in bounds of a prime number, in your proof you took the epsilon. Okay.
Yes.
Sir, can you tell me what is how to find the epsilon? How you know the epsilon? Then you will get bounds, right?
No, actually, no. What we're not finding epsilon. So what we're saying is that okay. So how?
Okay.
So here the Ramanujan prime is close to the 2n prime. I know, but when you see how close we can go to 2n prime. Now closeness means so there epsilon is coming to equal. So choose any epsilon positive. It can be minus. It can be 0.1, 0.001, or 0.0001.
Sir, my doubt is the choice of epsilon is in our hand, right?
In our hand, yes.
Okay, sir. Okay, sir.
Yeah, that's right.
And then you will get that bounds of the prime number that approach means near to the prime.
If you choose epsilon, then I get some n naught. But whenever n is bigger than n naught, then the Ramanujan prime is very close to 2n plus epsilon n naught. That's what.
Okay, sir. Thank you so much, sir. Sir, I want to contact with you, sir. Can you provide your email?
Yeah. So,
yes. Thank you so much, sir.
Thank you, sir. We have one more faculty member, Dr. Prasad T. He was here. Prasad is not here. You might have.
How many?
Now, 5, sir.
Oh, 5.
Dr. Prasad and Mubina just joined.
Okay.
This time.
So hopefully, when I visit KSM next time, I will.
Okay, sir.
Visit you.
We will. Good. Thank you, sir.